The density of a substance is important. You can actually separate substances by their differences in density. So density is a relationship between the mass of an object and the volume it occupies. So the mass is usually in grams, and the volume will be milliliters or centimeters cubed. So you can see on the right-hand side there, gold has a density of 19.3 grams per centimeter cubed. The mass, so in 1 centimeter cubed or 1 milliliter, remember they're the same thing, you have 19.3 grams of gold. Now mercury, the lower part there, is 13.6 grams per centimeter cubed. So that means in a centimeter cubed or a milliliter, you're going to have 13.6 grams of mercury. So the density of the two is different. Now substances will a lot of times align themselves. The more dense things go to the bottom and the less dense things go to the top. They call it superposition sometimes, and that can be very useful when you want to separate out different substances. So here's a video showing Diet Pepsi versus Pepsi in water.
First, the can of Pepsi is dropped into the water. Note that the can sinks. Now the can of Diet Pepsi is dropped into the water. Note that the can floats. What causes the difference in densities? Pepsi contains sugar and Diet Pepsi contains aspartame. Sugar solutions are more dense than aspartame solutions.
Aspartame, which is also known as NutraSweet, is used in a lot of diet drinks, and it has a different relationship with the water in the Diet Pepsi than sugar does with the water in regular Pepsi. So you can actually separate them out using that system. So here's an example of a problem you might see. Let's say that you had polypropylene rope, which is used when you're water skiing. You hold on to that rope and stuff as the boat pulls you around. Polypropylene floats on water, and soda bottle plastic, which is made from a compound called terephthalate polymer, you don't need to worry about that, sinks in water. So the question is, what's the order of increasing density, i.e. which one is the most dense, which one is the less dense? Well, the less dense thing will be usually on the top, and the most dense thing will be on the bottom. So because the rope floats, that's going to be the least dense, the polypropylene. Water would be in the middle, and then the most dense, the part that sinks, would be that soda bottle plastic. So answer B here would be the right way. Because one floats and the other one sinks, that's why they have different densities. You can use this to separate out plastics while recycling, which is kind of a cool concept that's used sometimes. Here's a problem where we can actually use density in some interesting ways. Let's say that we have a piece of copper. It has a mass of 57.54 grams, and our piece of copper is rectangular. It's 9.36 centimeters long, it's 7.23 centimeters wide, and it's 0.95 millimeters thick, so not very thick. But let's say we wanted to calculate then the density of the copper, and density is usually in grams per centimeter cubed or grams per milliliter, either way. Solids are usually measured in centimeters cubed for volume, and liquids usually have milliliters, but you can interchange them if you want to. That's not written in stone, but that's what usually happens. Well, no problem. What we're going to do here, we're going to take the mass, the 57.54 grams, that'll be our numerator, and in the denominator, the bottom, we want the volume. And volume here will be centimeters times centimeters times centimeters, but one of our units right now is in millimeters. So the first thing we need to do is convert the millimeters into centimeters. And earlier, I showed a thing where there was 10 millimeters per centimeter, so 0.95 millimeters would be 0.095 centimeters. And now that we have that unit in centimeters, we can multiply those 3 centimeter values by each other. So length times width times height, essentially. They have to all be the same unit, though, because we want centimeters cubed out of it. If we left it in millimeters, first of all, the answer would be different, and the units would be centimeters squared times millimeters, which is kind of awkward. So we want to have just centimeters cubed for volume, and that comes out to be 6.4. And again, I'll talk about why we're rounding them here in a little bit. And then finally, the density of the copper would be mass in grams over volume in centimeters cubed. That's going to come out to be 9.0 grams per centimeter cubed. And this is how they could figure out the density of this metal. And you could do this for any metal. It's a nice way to sometimes confirm if you have the right metal or not. You can look for the right density. Pretty cool. Here's another kind of problem. This one is based around what's called the Archimedes principle. And Archimedes was pretty clever. He was a scientist that figured out, hey, water displacement would be a great way to find the volume of an unknown solid. So for example, in this problem, we have a solid, but unlike the last problem, we don't have a nice length, width, and height. All right, a lot of solids come kind of messy. If you ever looked at rocks outside, that's kind of how this works. So the question is here, we've got some kind of piece of metal. It's 33.2 grams, and that you can measure on a scale, so that's not a problem. But we don't know the volume, and we don't have a nice length, width, and height. So what we're doing is we're starting with 10 centimeters cubed of water on the left, and when you add the metal in, you can see how the metal plus water combination goes up to 22.3 centimeters cubed. So the metal displaces the volume from 10 to 22.3 centimeters cubed. And in Archimedes' principle, then, you can take that final volume with both, subtract the volume of just the water to find the volume of your unknown metal. So in this case, the volume of the metal, we're not going to do length times width times height. We're going to do 22.3 minus 10 to get 12.3 centimeters cubed. That's the volume of the metal. And we have the mass of the metal. So the density of the metal, mass over volume, 33.2 divided by a total of 12.3, the density comes out to be 2.70 grams per centimeter cubed. And if you look at that table there, then it's going to be answer E. We have a piece of aluminum. Woohoo! Supposedly Archimedes figured this out while in the bathtub. I don't know if this is true or not, but Archimedes sat in there and he realized that he displaced the water, and they can use this then for finding fake gold. Apparently the king, wherever Archimedes was living, was having a problem, fake gold versus real gold. People were selling fake gold as real gold, and of course that's a drag. So Archimedes realized that you could use this displacement method. Fake gold is nowhere near as dense as real gold, so it would have a different effect on the water, and Archimedes saved the day. All elements have a different density, as well as compounds, etc., etc. This is a graph just kind of showing some of the densities of them. You can see that the kind of yellow-orange ones there, most of those are pretty small densities. Then you start getting into some bigger ones, and then finally some of them have very, very large densities. Now, some of these densities I'm a little skeptical. So in the kind of lower right-hand corner, there's AT, astatine. It claims it has a big density. I'm a little skeptical of that value. But anyway, you at least get the idea that all elements have their own density, and compounds do as well. So it's not that the density is the best way to identify an element or compound, but it can be a useful tool when people are analyzing compounds they don't know what it is, stuff like that. Here's another kind of problem you might see. In this case, we have mercury. Now, mercury, if you remember from earlier, is a liquid at room temperature and pressure. So in this case, we have 95 milliliters of mercury, all right, because this is a liquid. And again, liquids are usually recorded in milliliters, but if you wish to call it centimeters cubed, that's fine too. Well, mercury has a density of 13.6 grams per centimeter cubed. What is the mass of mercury? And if you want, you can record it in grams, or if you want to go to pounds, you can too. This is an example of what's called dimensional analysis, which sometimes is called factor label, has different names, but it's when you want to convert one kind of unit into another. And in this problem, we want to convert milliliters, our starting unit, into either grams or pounds, our ending unit. And if you do that, you need a conversion factor or a factor in order to convert one from the other. So we're going to use the 13.6. That's a relationship between the grams mass of the object and the centimeters cubed or volume of the object, which is really cool. And again, along the way, remember that milliliters and centimeters cubed, same thing. If you remember that a centimeter cubed and a milliliter are the same, you can use dimensional analysis then to calculate the mass. So 95 centimeters cubed times the density, 13.6 grams per centimeter cubed. You can see on there what we're doing. The initial unit is canceling out. Now in math, 5 over 5 equals 1, or x over x equals 1. Well, in this type of world, a centimeter cubed on the top cancels a centimeter cubed on the bottom. So centimeters cubed over centimeters cubed also equals 1, if you will. That means the centimeters cubed unit is gone. And the unit that's left, grams, is what's going to happen. So this comes out to be 1.3 times 10 to the third grams, or about 1,300 grams. I'll talk about why we're rounding here in a little bit. So that would be the mass of the mercury in grams. And if you wanted to know it in pounds for whatever reason, no problem. We can now use the conversion of 454 grams equals 1 pound. So again, notice here on these factor label, you're starting with one type of unit and converting to another. In the last one, we went centimeters cubed to grams. In this one, we're going to go grams to pounds. So we'll take the grams, we'll use the conversion of 1 pound over 454 grams. You can see how grams on the top cancels grams on the bottom. In your calculator, you'd go 1.3 times 10 to the third divided by 454, and you'd end up with 2.9 pounds of mercury.